In section 5.3, we're going to look at Riemann sums and definite integrals. To start, let's do example 1. Consider the region bounded by the graph of f of x equals the square root of x and the x-axis for 0 less than or equal to x less than or equal to 1. Let's evaluate the limit as n approaches infinity of the sum from I equals 1 to n of f of ci times delta xi, where ci is the right endpoint of the partition given by ci equals I squared divided by n squared, and delta xi is the width of the ith subinterval. So this is what we want to evaluate. We're going to take the limit as n approaches infinity of the sum from I equals 1 to n. This is going to be f of ci. So we're taking the function f, which is the square root function, and we're evaluating it at these inputs. So the f of ci, that's going to be the square root of I squared divided by n squared times delta xi, which is the width of the ith subinterval. So the way these intervals are set up, they don't have a constant width. The width kind of changes. The delta xi, if we look at the width of the ith subinterval, notice that ci is the right endpoint of an interval. So the width of these would be ci, the right endpoint of one interval, minus ci minus 1. That is, it's going to be equal to ci, which is I squared over n squared minus ci minus 1, which would be I minus 1 squared over n squared. Let's try to simplify this as much as we can. This is I squared over n squared minus, if I expand this numerator here, that's going to give us I squared minus 2i plus 1. I squared minus I squared will cancel, and then if you distribute that negative through, we're going to get a 2i minus 1. So what is delta xi? Delta xi is 2i minus 1 divided by n squared, and that's the second term that's going to, or the second part of the sum that's going to go in here, times 2i minus 1 over n squared. So this is what we have to evaluate. Let's try to simplify the summand. The limit as n approaches infinity of the sum from I equals 1 to n. This square will end up canceling with the square roots. So we're going to have an I over n times 2i minus 1 over n squared. This is equal to the limit as n approaches infinity of 2i squared minus I in the numerator, all divided by n cubed. I don't want to forget to write the sum. Remember, this sum is over n. Excuse me, the sum is over I meant to say. So the 1 over n cubed, that can be factored out of the sum. Like this. Two I squared minus 1, minus I. And now we can use some of our summation formulas in order to find these pieces here. This is going to be the limit as n approaches infinity. we still have this multiplication factor of 1 over n cubed times 2i squared. So I'm going to keep the 2 here. If you go back in the notes to our formula for the sum of the first I squareds, so the first n square terms, it's going to be as follows. That's going to be n times n plus 1 times 2n plus 1 all divided by 6 minus, coming over here, the sum of the first ni terms from I equals 1 to n, the sum of those first n numbers, is going to be n times n plus 1 all divided by 2. I'm going to skip a little bit of algebra, but if you kind of expand, distribute everything through, we will, and then break apart the fractions, we're ultimately going to get 3 terms. This will be the limit of 4n cubed plus 3n squared minus n all divided by 6n cubed, which is the limit as n approaches infinity of 2/3 plus 1 over 2n minus 1 over 6n squared. As n goes towards infinity, this is a constant, so that stays the same. 1 over 2n will approach 0. 1 over 6n squared will approach 0. So in the limit, we get 2/3 plus 0 minus 0, which is just 2/3. Okay. So that's our final answer. The area under the curve of the square root of x from x equals 0 to 1, that area is exactly 2/3, and we found it by doing Riemann sums. The good news is this is not how typically we're going to be computing areas moving forward. Especially as we move into the next section, there's going to be a shortcut to this, much in the same way if you remember back when we first learned how to do a derivative, using the formal definition as a limit. This is the formal definition of a Riemann sum for how to find area. There will be a much faster and efficient way that we will focus on in terms of finding areas in a moment. Just to kind of recap, though, some of the ingredients that were at play here. The definition of Riemann sums. Let f be defined on the closed interval a to b, and let delta be a partition of ab. In other words, it's taking the interval a to b, and we're breaking it up into n subintervals. The first one starts at x sub 0, which is equal to a. The x sub n is going to be equal to b. And we have these sequence of x1s, x2s up to xn minus 1 up to xn. They're in between those. Delta xi will represent the width of the ith subinterval. So we have our a, we have our b. This is the partition step where we're taking and we're breaking this up into a bunch of subintervals. Delta xi represents the width of that ith subinterval. And then the next thing we're going to do is we're going to pick a selection point. So we partition, we select a CI, which is in that ith interval, and then we evaluate the function at f of CI. Thinking back to the area of our rectangle, this would be like our length times our width. So each individual element inside of the sum would represent the area of a rectangle whose width is delta xi, the length of the ith interval, and whose height is given by the function evaluated at the selection point ci within that interval. If we do this for a point ci and within each of the intervals and sum them all up, what we would get would be an approximation of the area under the curve of f from a to b. This is called the Riemann sum of f for the partition delta. We define the width of the largest subinterval of a partition is called the norm, and it's denoted with the partition in between two sets of vertical bars. Again, the norm here is it's the maximum delta xi. So the width of the largest subinterval, that's referred to as the norm of the partition. For a general partition, the norm is related to the number of subintervals in the interval a to b in the following way. If you take the width of the interval, which is b minus a, and you divide it by the norm of the partition, this will be less than or equal to n. So the number of subintervals in a partition approaches infinity as the norm of the partition approaches to 0. That is, as the norm approaches to 0, this will imply that n will approach infinity for regular partitions. Okay. This is a little bit of a technical thing that we're not going to focus on so much in our class, but the proper definition here should really be the norm of the partition approaching to 0 to get the true area. Because what I mean by that is it's possible where maybe you have an interval a to b, and you could partition this thing. You could, in a weird, wacky kind of way, go ahead and create an infinite number of partitions by simply maybe breaking up, parts of the interval more by putting more and more and more subintervals. But unless that goes across uniformly, in other words, unless the norm goes to 0, in other words, the width of the largest subinterval, then you're not going to capture the true area under the curve. So if the norm goes to 0, then that certainly will mean that the width of each of those subintervals goes to 0, which means that the limit of our Riemann sums would approach the true area under the curve from a to b. I will leave this up to you all to read, but this is the definition of the definite integral in terms of what it means for that limit to exist in the usual epsilon delta sense. So, try to read over that if you will. We won't be doing epsilon delta proofs in our version of this course. This brings us to the definition of the definite integral. If f is defined on the closed interval a to b, and if the limit of the Riemann sums over partitions delta, we have the following. The limit as the norm of the partition approaches 0 of the sum from I equals 1 to n of f of ci delta xi exists, as described above, then f is said to be integrable on the closed interval a to b, and we are going to denote this limit by the following thing. This will be the definite integral from a to b of f of x dx. So when a function is integrable, in other words, when the limit of these Riemann sums exists, then the function is called integrable on a to b, and we will use this notation, which is going to be called the definite integral. This is read the integral from a to b of f of x dx. We saw this notation back when we were doing antiderivatives, or indefinite integrals. Here what we have is an integral that has a lower bound of a and an upper bound of b. It's always the case that the left bound, or the lower limit, goes down here. That's the leftmost point in your interval. And then the rightmost point, which is the upper bound, goes on top. One of the conditions that for most applications we will come across is going to be sufficient for us is that if you have a function that's continuous on a closed interval, then it will be integrable on that interval. So Theorem 5.4, continuity does imply integrability. A function on a closed interval that's continuous will also be integrable on that interval. This is nice because we saw that back when we were doing differential calculus, continuity was not a sufficient condition to ensure differentiability, right? We had functions that were differentiable, but not continuous, but not differentiable. But at the same time, continuity will imply integrability.